There are lots of applications for derivatives. Most of them involve rates of change. Remember, we talked about that if we have the slope of the secant line, which we wrote with this equation, then we get an average rate of change. So if we have 2 points, we find their values, their x values, and then their function values, their y values, and we could find the slope of that secant line, and that would give us an average rate of change. And then we said if we take the limit as h goes to 0, so if these points get closer and closer and closer together, then we would have an instantaneous rate of change. So we're going to use that to find some ways to calculate rates of change for all kinds of different things, including particles in motion and how they change, and things in economics like cost and revenue and things like that. So let's start looking at some examples. What if we want to find the rate of change of the area of a circle with respect to its radius? Now this is where those differential notation helps, because if we look at this, we're finding the rate of change of the area with respect to the radius. So if we write that out, this instantaneous rate of change is a d. Remember, it comes from the lowercase delta because we use change as the capital delta, that triangle looking thing. So we have the rate of change of the area with respect to its radius. So if we look at this sentence and change it into this differential, we can tell what we're looking for. So we know that the area of a circle is pi r squared. And what we want to know is if we have this circle, how is this area changing as the radius changes? So when the radius changes a little bit, then we get this new area. And how does that look in an equation? Well, this is what we're looking for. We turned our sentence into a differential. So we know that what that means is we're looking at this derivative of the area formula with respect to the radius. So we use our power rule, and there we have it. This is the rate of change of the area of the circle with respect to the radius. Now notice this is the circumference formula, and we're going to, I think we've talked about why that works and everything with the little sliver here of space that changes. But that happens a lot with these areas and volumes and those kind of things versus surface areas or circumference, perimeter, that kind of stuff. So kind of pay attention to that as you're learning things. Like, for example, if we want to find the rate of change of the volume of a sphere, with respect to its radius. Now again, let's change the sentence into a differential. We want the rate of change of the volume with respect to the radius. This is what we're looking for. So we know the volume of a sphere. Yes, you are expected to know all these areas and volume formulas that you learned all over the rest of your schooling. So we take the derivative, use that power rule again, and we get 4 pi r squared, which you'll notice is the surface area of a sphere, which we've also kind of talked about. So that's how we do our rate of change. Take those sentences and change them into a differential so you can see what you're looking for and then start using your formulas. Now, what about this motion along a line, or the particle movement? Particles' position is usually given with an S of t. So this is position in terms of time. Now, your average velocity is going to be your displacement, or your change in position, divided by the time that you travel. So that's your change in position over your change in time. Now, notice I'm using a capital delta here at the triangle. That means that we're looking for average. So if you have position, then you find the average when you move from, say, 5 meters to 10 meters, then your displacement is 5 meters, because that's how far you've moved, and how long it took you to get there is your time traveling. And that would be your delta, and that'll give you your average velocity. But what if we want the instantaneous velocity, right? Instantaneous. I'm never sure if I'm spelling that right, so just keep an eye on it. Your instantaneous velocity is going to be the derivative, this lowercase delta, which we just write as a d. Now, this gives you the instantaneous velocity right at one particular time. So if you want to find the velocity at t equals 2 seconds, you're looking for an instantaneous velocity, where if you said, I want to know what the velocity is from t equals 2 seconds to t equals 4 seconds, that would be an average velocity. So an instantaneous velocity is where we find the derivative. Now, the things that you need to remember about velocity: if you have a positive velocity, that's different from a negative velocity, because that gives you your direction. For example, a positive velocity means you're moving to the right on a number line, and a negative means you're moving to the left. Or if you're throwing a ball in the air, a positive velocity means you're moving up, and if a negative velocity means you're moving down. Now, speed and velocity are a little bit different, because speed is the absolute value of the velocity. Okay, you don't have this direction. The direction is with velocity, not with speed. If you're taking physics, or you've taken physics already, then you've gone over all of this. So our velocity function is written v of t, and it's the derivative of the position, which you can also write with a differential notation, ds dt. Now, what about acceleration? Well, acceleration tells you the instantaneous change, or the change in the velocity. So you can use this. You have your average acceleration would be your change in velocity over that time and how long it would be. Or your instantaneous acceleration, you would use your differential, because you want it right there. So it's the derivative of the velocity. And you write that a of t is the derivative of the velocity, which means it's the second derivative of the position. It's really important that you remember this, okay, and that you understand why. Okay, the velocity is the instantaneous rate of change of your position, so it's a derivative. The acceleration is your instantaneous rate of change of your velocity, so it's a derivative. So that's your physics application lessons for today. One little thing that you also need to know, this formula. If you have a free fall, then you have your position formula is 1/2 the acceleration due to gravity times time squared. And gravity, there's 2 that you need to have memorized. And like I say, hopefully you've taken physics, or you are taking physics, and you've gone over this some. Pay attention to your units, but these are the 2 gravity constants that you need to know: 32 feet per second squared, or 9.8 meters per second squared. make sure you pay attention to your units. So, and what this will tell you is your velocity, take the derivative, is gravity times time, and of course your acceleration is just gravity because we're just free falling, it's not being pushed at all. The other thing that we can look at, other than particle movement, is the economic equations. And next semester, you'll probably be taking economics, and you'll learn some of this, I think, but some of this may be a little beyond the scope of that class. The biggest thing that you need to understand is when you're talking about cost, you're talking about an average. And when you're talking about marginal cost, that's an instantaneous. How much does it cost to make that one more? And the same thing with revenue, actually. Revenue, you would have an average. If you have marginal revenue, that's an instantaneous. Am I even spelling that right? Revenue. All right, so you would have, for example, if you have a revenue equation, for example, let's say it's r of x equals 2,000 times 1 minus 1 over x plus 1. If you have this revenue equation here, then if you want the marginal revenue, so this is the revenue equation. If we want the marginal revenue, then we're going to take the derivative of this, which we've got this constant. The derivative of 1 is 0. So we got the derivative of this one. We got to use our power rule. Remember, this is x plus 1 to the negative first. So that'll give us, take down the power, 1 over x plus 1 squared. So we get 2,000 over x plus 1 squared. This is our marginal revenue. So what this tells us is the average revenue for a certain number of things sold. Say you sell 5 things, then the average revenue for that you would plug in 5. If you want to know what the marginal revenue is, or the revenue for that 5th one when you're going up, you'd plug in 5 here. So the cost and the revenue, the thing you need to know the most is that marginal. That word marginal means that you're moving to an instantaneous, which means you're going to move to a derivative. And we'll talk some more about those in class. So make sure you've read this section. There's lots of good examples in the book for this kind of stuff and some things that you need to know about that. Written down any questions that you have. Make sure you understand about the difference between average and instantaneous, how to calculate those, that you understand about particle motion, and that you understand at least the difference between the revenue and cost and the marginal revenue and cost.